Hello, my name is Lori, and in this video I'll be explaining Kepler's laws of planetary motion. Kepler developed 3 laws, and although this video will prove only the second and third law, these proofs require some concepts from the proof of the first law, which states that a planet revolves around the Sun in an elliptical orbit with the Sun at one focus, as you can see in the figure. The first law defines the vector r cos theta r sine theta 0, to be the position vector, as it represents the position of the planet as it orbits around the Sun. The vector u is the unit vector in the same direction as r, and is represented as cos theta sine theta 0. Kepler's second law states that the line joining the Sun to a planet sweeps out equal areas in equal times. To illustrate this, if the time it takes a planet to move from position A to position B is equal to the time it takes a planet to move from position C to position D, then the first area must be equal to the second area. To start, we begin with the constant vector h, which is the cross product of the position vector r and the velocity vector v. From the proof of the first law, h is also equal to r squared times the cross product of u and u prime, where u is as defined previously, and u prime is equal to minus sine theta cos theta 0 d theta by dt. The magnitude of u cross u prime is defined as the magnitude of u times the magnitude of u prime times the sine of the angle between the two vectors. The magnitude of u is 1, the magnitude of u prime is d theta by dt, and because u and u prime are perpendicular, the sine of the angle is 1. This gives only the magnitude of the cross product. It is also necessary to determine a direction. From the diagram, you can see that u and u prime lie in the xy plane. The cross product of two vectors is a perpendicular vector, so the cross product of u and u prime must point in the z direction. This is represented by multiplying by k, a unit vector in the z direction. Knowing the cross product of u and u prime allows this expression for h to be constructed. Taking the magnitude of both sides of the expression allows the scalar h to be expressed as r squared times d theta by dt. The area swept out by a curve in polar coordinates is equal to the integral of 1/2 r squared d theta. By substituting the expression for h, the area can be expressed as the integral from t naught to t of 1/2 h dt. Taking the derivative of both sides gives dA by dt equals 1/2 h. Writing this in terms of r gives dA by dt equals 1/2 r squared d theta by dt. Returning to the expression dA by dt equals 1/2 h and integrating both sides yields a equals 1/2 h t minus t naught. This proves Kepler's second law. As long as the time interval t naught to t is equal, the area swept out will be constant. Kepler's third law states that the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. In the diagram, the major axis is represented by the blue line that intersects the two foci. Beginning with this expression from the second law proof and rearranging it, you can see that dA equals 1/2 h dt. If the left side is integrated from 0 to a, representing the area swept out in one revolution of the planet, and the right side is integrated from 0 to t, representing the time it takes to complete one revolution, the expression a equals 1/2 ht is obtained, which can be rearranged and expressed in terms of t. The area of an ellipse is pi ab, where a is the length of the semi-major axis of the planet and b is the length of the semi-minor axis of the planet. Therefore, the period of the planet's revolution is equal to 2 pi ab over 8. This expression for r was generated as part of the proof of the first law. From it, it can be seen that h squared over gm equals ed, where g is the universal gravitational constant, m is the mass of the sun, e is the eccentricity of the ellipse, and d is the directrix. Using properties of conic sections, it is also possible to determine that b squared over a is also equal to ed. This leads to the conclusion that h squared over gm equals b squared over a. Rearranging this expression gives h squared equals gm b squared over a. By returning to the original expression for t and squaring both sides, and then substituting this expression for h, it becomes evident that t squared equals 4 pi squared over gm times a cubed. This proves Kepler's third law, as the period t is proportional to the major axis cubed, as 4 pi squared over gm are all constants independent of the chosen planet. Kepler's laws are useful for calculating distances in space. For example, to determine the length of the major axis of the Earth's orbit, you would write the expression for t in terms of a, the length of the semi-major axis. The period of the Earth's revolution is 365.25 days, or 31,557,600 seconds. The mass of the Sun is 1.99 times 10 to the 30 kilograms, and g is equal to 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. This results in a semi-major axis length of about 1.5 times 10 to the 11 meters. To obtain the length of the major axis of Earth's orbit, multiply this value by 2, giving a length of 2.99 times 10 to the 11 meters.